Today's speaker is Ron Smith, the Damon Wells Professor of Geophysics. He's also the director of the Center of Earth Observation. He's also a smart guy. And he won an award for teaching, and I couldn't find it. I don't know. What was the name of that award?
I don't know either.
Best Teacher Award of the Year.
That was it, I'm sure.
Yeah, and his focus is meteorology and regional climate, and he does lots of things. One of the things he spends his time on is satellite remote sensing of landscape changes and climate sensitivity, which will feed into his talk today. And his current projects involve satellite analysis of surface climate feedbacks, which I believe will feed into his talk today. And the title of his talk is Surface Impacts and Climate Feedbacks in the Texas Drought of 2011.
Thank you. Okay, so this is work that is still in progress. So any comments or questions you have would be very valuable as we try to wrap it up. We are, for some time, have been interested in various climate feedbacks, and you probably already know what I mean by that, but let me try to put some flesh on this idea of a climate feedback. One well-known one, snow albedo feedback, is where you might have a colder climate that would shift precipitation from rain to snow. The snow lying on the ground increases the albedo of the Earth, which reflects more sunlight, which cools the climate further. That would be an example of a positive climate feedback. A water vapor feedback would be you warm the climate, you evaporate more water. The warmer temperatures allow more water vapor to be held in the atmosphere. Water vapor is a greenhouse gas, traps more outgoing long-wave radiation. You warm the climate further. That's another positive feedback. On a longer time scale, a carbon stocks feedback where a warmer climate will drive CO2 out of the oceans, maybe drive CO2 sequestered in permafrost out of the land surface into the atmosphere, more CO2, more warming, warmer climate. Those are examples of positive feedbacks where the feedback loop increases the amplitude of the climate anomaly. The one I'll be talking about today is this last one, less well known than the others. Well, for one reason, it can work two ways, and we're not sure which way is going to dominate. If you have a heat wave or a drought, that's going to change the nature of the vegetation on the landscape. Most likely, that's going to turn, say, green grass to brown, or short grass to barren soil. In either case, that's going to have an influence on the albedo. Generally, when you brown out the grass, or when you replace grass with bare soil, you increase the reflectivity of that surface. That is to say, you increase the albedo. That by itself would reflect more solar radiation and would have a cooling effect. That would be a negative feedback. On the other hand, when you have a heat or a drought wave, you reduce the amount of water available to plants. There's less evaporation. Now, when the Earth receives radiation from the sun, it then partitions it primarily into either sensible heat going into the atmosphere, that is just warm air rising, convection, radiation carrying that heat quickly into the atmosphere, or evaporation, evaporating moisture at the surface and carrying the water vapor upwards, but not directly heating the atmosphere, at least locally. The idea here is that in a drought, you would change the partitioning between sensible heat and latent heat fluxes in favor of sensible heat fluxes. That would cause a warming of the lower atmosphere. That would be a positive feedback. So we're going to be looking at this last one today, trying to decide which one of these is dominant. These feedbacks can be investigated, I guess, using any change. You can investigate any change in the Earth's surface. It could be the seasonal cycle. It could be interannual variation, one year wetter or drier than the next. it could be longer climate change. Today, we're going to be looking mostly at interannual. We're going to be looking, in fact, at a single event, the Texas Drought of 2011, and see if we can deduce what the nature of the climate feedbacks were in that event. So this headline, and many like it, you may recall from just about 1 year ago. This was all the rage in the newspapers a year ago, the Texas Drought. And this is the one we'll be talking about today and its implications. Surprisingly, or perhaps disturbingly, I'm not going to try to explain why this drought occurred in the first place. That's actually a very difficult question. I am going to point to a couple of possible attributions of it. This new subject of trying to take a climate or meteorological event and understand why it happened is now called the science of attribution. And it's very new, and I must say, I don't think very well developed. We don't have good tools. The atmosphere and the ocean have such randomness to them that for all we know, a drought could occur just by a chance superposition of a long string of dry days. It might not have an actual detectable cause. But I'll mention these two. So it has been known from previous investigations that El Nino has an impact on certain zones around the world in terms of their climate. For example, when El Nino occurs, it is generally thought to be warm in some regions, wet in others, and the opposite is true. When you have La Nina, that is colder conditions in the tropical Pacific Ocean, then you get the opposite side of this. So let's look at the time record of the ENSO record here. During the 2011 period, we had generally a dominant La Nina cycle, cold temperatures in the tropical Pacific. So you would flip this and say that you might expect to have a warm, maybe even a dry condition, but not a wet condition in the Texas area. Also, that little region of significant climate effect of El Nino is not exactly covering Texas. So I would say one could perhaps draw an idea from this diagram, but not at all be certain that that Texas drought from last year was caused by the La Nina. Another line of thought would be to say, well, maybe this is something to do with global warming. Maybe as the world warms, that there will be local climate anomalies that will be wet or dry. So this comes out of the IPCC, and it's soil moisture anomalies. This one for the middle of our starting century, and this one towards the end, under, I don't know which scenario it is, but under one of the global warming CO2 emission scenarios. And you will notice a tendency for drying in the Texas region on both the short 50-year and the 100-year time scale. But again, to attribute a particular drought to this kind of a global warming trend, I think is exceedingly difficult at this stage. Our knowledge simply isn't up to that challenge. So that's not going to be my focus today. It's rather going to be to look at local feedbacks. Accept this as an accident or an act of God, whatever you prefer, and then look at the impacts on that region of the world. So this is it. So just a year ago, if you went on to the NOAA website for drought monitoring, you would see this diagram. And they've got a color code there: moderate, severe, extreme, and exceptional. The brown color is coded to mean exceptional, by which they mean there perhaps has never been a drought quite this extensive in that region since measurements began. There's a mix of brown and red colors in there, but no one would argue that that wasn't, if not the most the strongest drought in Texas over the last several decades, at least one of the strongest droughts. Remember, this is a cumulative measure. So drought on this scale is a combination of having below average precipitation over an extended period of time. It might also be a measure of soil moisture, however, which roughly depends on the same things. Below normal precipitation over an extended period of time. Little did we know that just a year ago that today we'd be looking at a drought map like this. This was from just a week or so ago. And we had quite a remarkable drought in the center of the country this year also. So these are coming now in, seems like in rapid succession, but they're all different. In fact, I read in a paper recently that the four of the strongest droughts on record have occurred just in the last decade. They would be the heat wave drought in Western Europe in 2003, the Eastern European and Russian drought of 2010, the Texas drought of 2011, and this one of 2012. So this is almost now a rapid fire occurrences, perhaps somewhat randomly around the globe, of severe summertime heat and droughts. By the way, stop me if you have questions. I'd be happy to take your questions.
Does the Georgia drought rank on that? Is there one of the top five?
I think the Georgia, that's what I meant by the Eastern European Russian drought, yeah.
No, I'm thinking the one in Georgia.
Oh, no, that wouldn't rank on that scale. No, that was too local and not sufficiently deep. So we're going to be looking at Texas, and Texas is renowned for being a big state, and I want to remind you that it is indeed a big state and not uniform. So you have to remember, when you look at a drought map like this, the drought may have covered most of the state, but actually there is more than one climate zone as you come across Texas. For example, there's the Köppen, the famous Köppen climate scheme is there, and it shows a rather major break between West Texas and Central and East Texas. And furthermore, when you look at the forest cover for the United States, which is also a reflection of regional climates, you have forests in East Texas, but not in Central and West Texas. So there's a climate zone across the state, and we're going to use that to our advantage because we're going to be able to use that single event, the Texas drought of 2011, to look at climate impacts in 3 different climate zones, all within the state of Texas. A bit of precip data, just to set the stage. So we've looked at these 3 regions here in Texas, West Texas, Central Texas, and Eastern Texas. Here's the rainfall data for West Texas. 4 data sets are shown. Let's see, the black symbols are the so-called reanalysis data for that particular region of Texas for a normal year. The red is the same reanalysis data for the year 2011. You see there really was a strong precipitation deficit in that year. Just to check that, we've taken the weather stations shown here in the dots and averaged them together. In other words, we've done our own little climatological analysis, and those are the bar graphs. But those 2 agree pretty well. So no matter whether we do the data or we let the National Weather Service do the data analysis, we get about the same picture for that. And that is to say that at least in the first 8 months of the year, the precipitation was only about 15% of the normal for that part of the world. The same thing could be said for Center and East Texas, perhaps not as dry as West Texas, relatively speaking, but still 1/4 to 1/3 the precipitation. So an extremely strong drought in all 3 of these climate zones across Texas. Now the methodology today is primarily a space-based methodology. We're going to be looking at Texas by using orbiting environmental satellites. And these are the two we're going to be using, Landsat on the left, the MODIS sensor on the Terra satellite on the right. These two have very different characteristics, and we've used them in different ways to complement each other. Landsat has a very high resolution spatially, 30-meter pixel sizes. It can resolve, individual agricultural fields on the surface of the Earth, but it has a 16-day return time. It only takes a look at a certain place on the Earth every 16 days. And then with cloud cover, that turns into more like a 6-month or a 4-month return time. You only get a look, you come over every 16 days, but then it's going to be cloudy, and then maybe the third time you'll get a good view of the surface. So that's the advantage, but the disadvantage of the Landsat system. The MODIS system has a much broader field of view. The pixel size is a kilometer. We're not able to resolve small objects, but it gets a daily image. Clouds are a problem there too, but it means you probably get a good look at that surface every 8 to 10 to 12 days, something like that at the worst. And so you get pretty good spatial coverage, even in spite of the clouds. So we're going to be trying to use these two in a complementary fashion. Here's Landsat, for example. It's in near polar orbit, takes 99 minutes to go around the Earth, has a sensor on it that measures light received at the satellite in several different wavelengths, 3 bands in the visible, 1 in the near infrared, 2 in the mid-infrared, and 1 out there in the thermal infrared. We're going to be especially using these two. Well, we're going to be using all of these and this one as well. I should say MODIS has a similar array of sensors with even more wavelengths available. So to come down to the core of it, we're going to be using satellites to detect 3 different quantities that'll tell us something about the nature of the Earth's surface. First is the Normalized Difference Vegetation Index, NDVI for short, which is a measure of the density of green vegetation. I'll show you a diagram for how this is done. It basically uses the contrast between how red light reflects from the surface and how near-infrared light reflects from the surface. The second will be albedo. I mentioned it earlier. It's the net reflectivity of sunlight from the Earth's surface. So it's the reflectivity weighted with the emission spectrum for the sun's surface. So it's weighted with the radiation coming from the sun. And the last is the land surface temperature, so-called LST. I'll be using that acronym over and over again. It's basically measured by determining the intensity of thermal infrared radiation reaching the satellite, and then inverting the Planck function to find the temperature of the object that is radiating that energy. So just a bit more on the NDVI. Here's a typical plot of how 2 objects, actually 3 objects, reflect radiation. There's wavelength on this scale in microns, and the reflectivity in percent on the y-axis. Soils look like this. The reflectivity gradually increases with wavelength. But the most remarkable is green vegetation, which is fairly dark. By the way, the visible spectrum goes from 0.4 to 0.7 microns. So the human eye is sensitive right there. And vegetation is generally dark to our eyes. But just beyond the visible, right at 0.7, the reflectivity jumps up to a much larger value. So forests and grass and so on is actually quite a strong reflector at wavelengths just beyond the human eye. And we'll use the contrast between the near IR reflectivity there and the red reflectivity there to build the NDVI. It's green minus red over green plus red, and that's the NDVI. Now, this has been used for 30 years or more. These are typical values for NDVI. For example, dense vegetation reflects only 10% of the red, but half of the near IR. You put that into the formula, you get an NDVI of 0.7 roughly. Dry, bare soil, you saw the numbers, that's a lower NDVI. Clouds, they're very bright, but they reflect both types of radiation roughly equally. Therefore, they've got an NDVI close to 0. Snow and ice and water have negative NDVIs because they actually reflect more in the vis than they do in the NIR. So here's a plot for all of Texas of the MODIS-derived NDVI for about a 11-year period. The plus or minus 1 sigma curves here refer to the spatial variation across the state. So there's quite a wide variation about the mean. But let's look at the mean for a second. First of all, what you see mostly is the annual cycle. Lower in the winter, higher in the summer, but in some years with a multiple maximum, 2 maxes. I'm not sure I would say that there's a third one there, but in many years you see elements of a double NDVI maximum due to different crops, different land surfaces. It's not a simple smooth curve, even when averaged over the whole state. You see a little bit of this double pulse. I won't be saying much more about that. I just want to give you a sense of the quality of the data and what we can detect from it. But you might want to also notice the very last peak here, which is the summer of 2011. That's the drought that we'll be talking about today, a reduced vegetation coverage connected with that reduced precipitation. We can do the same thing for LST. That's the skin temperature of its radiative temperature, it's often called, the temperature at which it radiates. And once again, you see the annual cycle, winter to summer, winter to summer. And then in the last year, the drought year, you see a hotter surface than was ever present in the decade before, giving us more clues that the signal we're looking for is probably there in this MODIS data. So this is the questions we want to ask from it then. Can we detect and quantify the impact of the drought on land surface using this spaceborne technology? Do these changes modify the surface heat budget of the surface? Do they produce a positive or a negative climate feedback? And which land covers, which particular land cover types contribute the greatest change in that climate feedback? So the methods I'll be using are these. We've already talked about the first one. I've identified 3 different climate zones across Texas to give us 3 different possible responses. We're going to use the MODIS data to derive time series for NDVI, albedo, and LST. Oh, and by the way, from that, we're going to do some computations of the heat budget terms as well to quantify this in a more useful way. We're going to use Landsat, which has the smaller pixel size, to zoom in and be able to look at these changes by land cover type. And finally, we're going to use Landsat to create what we call change images, where we can see much more directly the role of the different land surface types on the climate response. So here's part of Texas. The coastline is down here. Oklahoma is there. The blue areas are ones where we summed over to get MODIS averages of LST, NDVI, and albedo. The orange squares were as close as we could come to that for our Landsat analysis. For some technical reasons, we couldn't get them to exactly overlay, mostly having to do with cloud cover. And then the little purple square there is where we were able to zoom in using Landsat, and I'll show you those at the end of the talk. You'll actually be able to resolve features on the ground and see what their contribution was to the climate feedbacks. So we're going to start with a MODIS analysis. This is stuff that Dea did as part of her PhD thesis. And there are 9 panels here. So the ones on the left are for West Texas, Central Texas, and East Texas. And then you've got the three variables that we're deducing from space: land surface temperature, albedo, and the vegetation index, NDVI. The blue are the average of the 10 preceding years. And there's some variability from year to year. And so to get some sense of that, we've put a 1 standard deviation, a 1 sigma plus or minus on there in the blue dash curve. And then the red data is the drought year of 2011. So let's first of all go across and look at the top panel. First of all, what you're seeing here primarily is the seasonal cycle in temperature. The land is colder in the winter, warmer in the summer. That amplitude is a little bit greater in West Texas than it is in East Texas. And in the 2011 drought year, we see a rather substantial extra warming. A little bit hard to read the scale, but that's approaching 10 degrees Celsius for an overheat on the surface in that particular year. It's that large also, maybe even a little larger in Central Texas, but generally smaller in East Texas, with the exception of late August, where we had that bump there. By the way, this time scale is simply day of the year, 1 to 365. The albedo is here. Normal years are in blue. The drought year is in red. And as we expected, the drought year, the surface got a little bit brighter. It's now reflecting a little more radiation. Check the scale out, though. It's not a huge amount. The albedo went from about 0.2 to maybe 0.22. Significant, but not huge in the albedo variation. And down here in NDVI, the blue is the normal, the red is the drought year, a rather dramatic difference, especially later in the year when the drought has had more impact on reducing soil moisture. Now let's just look at these all together then. So west, center, and east, I would say overall probably the center of the state has the biggest impact, although its albedo impact was delayed until the second half of the year. It's certainly larger than the east, maybe comparable with the west, but down here the albedo drop is large all the way across, and as I indicated, the temperature has the largest anomaly in central Texas. Smaller anomalies in eastern Texas. Now, from that data, we're able to do some rough estimates of the terms in the heat budget equation. And I want to talk about those here. Part of this format is the same, West, Central, and East Texas. But now what's plotted is the net radiation reaching the surface, the sensible heat, which is the convective and conductive heat into the atmosphere, and the latent heat, which is a measure of evaporation from the Earth's surface. What we do is deduce this from the satellite data, this from a combination of satellite data and surface data, and then this is computed as just to fill out the budget, in other words. We have to conserve energy, so that's computed at the end. Now, first of all, notice the difference across the state. In West Texas, you generally have less net radiation. Well, you see the seasonal cycle. Of course, that's due to this change in the sun angle during the year. But you see a difference from east to west across the state. That's due to, in part, the fact that West Texas has a higher albedo. Did I show you that? Yes. Look at the albedo going across the state. So more sunlight is reflected in the west and less in the east, typically. And that's why there's generally less net radiation in the west than there is in the east. Now, we split that apart and see how it partitions between latent heat and sensible heat. And, for example, starting in the west, almost 400 watts per square meter goes into sensible heat. Because it's a very dry landscape in a typical year, only about 50 watts per square meter goes into latent heat. Contrast that with East Texas. About 700 watts per square meter of net radiation. Very little of that goes into sensible heat. almost all of that goes into evaporation. So you have a very big swing in the way that the land surface balances its energy budget between East and West Texas. Let's now look at the anomalies for 2011. Let me just focus on Central Texas. There's too much to talk about in all of these. Okay, so by the time you get to August, you're seeing quite a reduction in net radiation in Central Texas compared to a normal year. And that is primarily due to that increased albedo. You're reflecting more of the sun's radiation. So there's less radiation to be partitioned between sensible and latent heat, but let's see how that partitioning is done. In spite of the fact that there's less radiation to be partitioned, the sensible heat actually climbs. There's more heat conducted and convected into the atmosphere, and the latent heat drops nearly to zero. Very little evaporation there. That partly answers the question that I posed in the very beginning of the talk about what kind of feedback we're going to get here. There is going to be an albedo effect. It's going to reflect more of the sun's radiation, but that is overwhelmed by a shift in the partitioning of how that net radiation goes into heating the atmosphere. I want to emphasize that. Was there a question?
Yeah, well, actually, you can go back to the previous one.
Yeah.
Just wondering if the, in the middle, the red graphs, are they just scale versions of the top one? And they more or less follow go to the top right?
Well, that's right, because this data is partly used to compute that. So there is a feed through from this data into that data, no doubt, yeah. Yep. So that idea, that basic idea is summarized here. I've summarized just for Central Texas late summer, just simplifying all that down to this one little region, this one little time. Got two diagrams. This is the normal year. That is to say the average of the 10 years preceding 2011, and this is 2011. Now, the red arrow is the net radiation. That's the sunlight that is absorbed. There's also some long-wave radiation in that, but I'm going to ignore that for the time being. It includes it, but I'm not going to talk about it. This basically is the sunlight absorbed, and that is reduced in the drought year because the surface has a higher albedo. Now, this energy gets partitioned. Notice the addition here, right? Those add to that. This adds to that. This energy has to be put back into the atmosphere. In a normal year, that's done mostly by latent heat, by evaporating moisture. And the sensible heat is somewhat smaller, important but smaller. In the drought year, however, that's primarily done by sensible heat. So in spite of the fact that there's less net radiation to be partitioned, there's actually more sensible heat. In other words, the surface is heating the atmosphere directly more in this case than it would be in a normal year. That tells us how those two feedbacks work. The partitioning is more important than the albedo. So to summarize this part of the talk, these three Texas regions have significantly different surface properties and heat budgets. The drought year had lower NDVI, higher albedo, and higher land surface temperatures. The drought year had lower net radiation due to a higher albedo, but higher sensible heat flux. That is to say, more warming of the lower atmosphere. And Texas in the center felt the largest impact of that. The sensible heat was up by a rather amazing 150 watts per square meter. That's a huge change in that surface heat flux term, sensible heat flux term. Now, we zoomed in with the Landsat to look at how the different land cover types responded. And this shows the summary for West Texas. Again, it's the same three variables. You should have these memorized by now: land surface temperature, albedo, and the vegetation index. Now this one's a little bit more complicated because we did it both for July and for August. So you actually see 4 bars here: a normal July, and then July of the drought year, and then a normal August, and an August of the drought year. In every case, especially in the July data, you see the LST jumps way up, except where you have water surface. Water responds in a very different way than a dry land surface would. The albedo jumps up as well in every case, more in some land cover types than others, and the NDVI drops. In each case, there's a drop going to the drought year. Again, more in some regions than others. And you get a similar contrast in regions when you look at central Texas. Here we only did it for August, so you just compare August of a normal year, August of a drought year. Notice that, except for the water, all of these are responding in a qualitatively similar way. There's not a great deal of difference. I'm going to be pointing out some differences that I think are important here, but you don't see it much in these diagrams. Perhaps, for example, the albedo goes up a little bit more for pasture land. But you know, the shrubland, it jumps up quite a bit as well. Not as much in the forest, not as much in the urban. You have to look at all these together to get some kind of a overall summary. And then for East Texas, this is the wetter part of the state. There again, we've only done it for August, so you find that the forests are hotter. They haven't changed their NDVI. Haven't changed their albedo, and they've dropped their NDVI just slightly. Here, the biggest impact seems to be in pasture land. You see it there in the NDVI, and you see it there in the LST. That's heated up more than these other areas. Something about pasture land with its shallow-rooted grasses makes it respond more strongly to the climate change that year. So, summarizing those, all land cover types were impacted by the drought except the water class. Somewhat of a difference from zone to zone. In West Texas, shrubland and rain-fed agriculture had the biggest response. Central Texas, shrubland and pasture. East Texas, generally it was the pastures that responded most strongly. We're going to try to illustrate that now. What I've got here are some Landsat zooms into a small region. That dimension is only about 11 kilometers. So we've really zoomed way into a small area. And I've got 4 images, 2 there, and then this 2 that go along with it. Let me run through that. So on the left, for a small part in West Texas, you've got a what's called a false color image. We used reflective bands beyond what the human eye can see to create a colored image that conveys some information about that scene. For example, band 7 in the mid-IR has been assigned to the red gun. Band 4, which is the near infrared, is assigned to the green gun. And band 2, which is in the visible, is assigned to the blue gun. So this is not true color, but it gives us more information than a regular visual color image would. And over here, by the way, is the terrain. There's a scale here. This is about a plateau about 900 meters above sea level. Down here, it's about 150 meters lower than that, with quite an abrupt terrain break here. In fact, you can see that reflected there in the nature of the vegetation in this part of Texas. Well, what do you see? The black dots are ponds, mostly farming ponds used to store water. The green circles are, of course, center pivot irrigation, which is the most cost-effective way of irrigation in West Texas. The rectangular fields, you see how they've got nice rectangular outlines. Those are agricultural fields that are in general not irrigated. That's generally rain-fed agriculture in those areas. And then down here you have some natural areas. It's rugged shrub and grasslands down in the southern part of the image. So we've got a nice mixture of land cover types, and we can see how the drought impacted those different land cover types. And that's what shows up here. So on the left, you've got the change in NDVI. Basically, you just subtract two images. You take the NDVI in 2011, subtract the normal year from it, and the scale is down here, hard to read, but 0 is there. Positive changes are red, negative changes are blue, and then on into purple. So this natural rangeland, probably should call it shrub and grassland, has had a slight drop in its NDVI. It's a dry year. The natural grasses probably didn't come out that year. Let's look at the human-altered landscape, which is all of this. The center pivot irrigation, some of it has a small change, some of it has a large change, depending on whether they put water on the field that year. The rain-fed agriculture is uniformly, well, not uniformly, because it still varies, but everywhere is strongly negative. In other words, there's been a big drop in rain-fed agriculture everywhere in this scene due to the drought. Corresponding to that are how the land surface temperatures have changed. The LST scale here, these are all positive values. That's 3.6 going on up to, I think, 18 degrees Celsius. There are some areas, large areas here, up in the rain-fed agriculture that had a land surface warming as large as 15 to 18 degrees Celsius. There were other regions where it barely changed at all, and of course you recognize that as some of those center pivot areas that were irrigated in the drought year. In spite of the fact that there wasn't as much irrigation water available, those farmers were able to get water to put on their center pivot irrigation, and therefore they've got a smaller response. So you're seeing at least those three things, right? The natural landscape, the rain-fed agriculture, and the irrigated agriculture responding differently to the drought. Stop me if you have questions on these. These are hard to look at if you're seeing them for the first time. Any questions here? Let's go on to central Texas. A very different landscape. Terrain is on the right. You see it's kind of an erosion pattern with higher terrain here, but a series of small streams merging to form a river going off to the northeast. You see that feature here in the reflected light as well. Again, it's a 742 RGB, a false color composite. There's a variety of vegetation patterns here, but the most remarkable thing, you would agree, is this dendritic pattern of the streams and the rivers. But they're dry most of the year. They're dry when this image was taken, certainly, and that land is very often grass covered, sometimes even grazed in the summertime, but not this year. It's quite barren this year. You see it as a bright white reflective surface because it doesn't have its normal riparian vegetation along those river courses. Let's see if that's reflected in our NDVI change or in the land surface temperature change. Now, here's the NDVI change. 0 is way up there, so these are all negative. So there's been a big drop in the vegetation index, but the strongest are these blue areas. Let me flip back and forth and we'll see where those blue areas are. Those are those riparian zones. Those zones that had water. This is a fairly dry climate, but those river courses have water in the summertime in them, but not in the drought year. And therefore the vegetation decreases rapidly there. Now let's look at the LST and see if that responds in a similar way. It does. It's right where you see the maximum drop in the NDVI that you see the maximum rise in the temperature. So less evaporation, because the vegetation in the water is not there, allows that surface temperature to rise after receiving heat from the sun. And we're going to do one last, and that's East Texas. Again, a very different landscape. The purple is pasture. The green is wetlands. And the forests of East Texas, the so-called piney woods of East Texas, are these darker areas up here. And here is the terrain. You can see that wetlands is in fact following a watercourse down here. The flow is from northwest to southeast. Let's see how these land cover types, pasture, wetlands, and forest, responded to the climate change. On the left is the NDVI drop, and it looks to me like the biggest NDVI drop is in this region. That's the pasture. Not every pasture, but generally the pasture land responds more strongly to drought in terms of dropping its vegetation. And with temperature, some of the highest increases in temperature are in this region, and also a little bit up into this region. Let's see what that was up there. See if that was also pasture. Yeah, I think it was, yeah. So there we've zoomed in and used the power of digital image processing to actually seek these changes as a function of land use, or if you prefer, land cover type. They each respond, and then the region is going to respond in total as a weighted sum of these different land cover types. So for example, in East Texas, where you have something like 33% forests, they've got a smaller response. That's going to give a lower response to the whole region as well. I think we can go on to summarize now, and then we'll leave some time for questions. So just to repeat, the methodology was to divide it up into 3 different climate zones to get more information, use a MODIS time series of these 3 satellite-derived quantities, go on beyond that to compute some estimates of heat budget term, and then use Landsat to zoom in and see what the different land cover types are doing. Here's what we conclude. The 2011 Texas drought indeed had a significant signature. We can see it easily from space. It's more than 1 standard deviation above the normal year-to-year variation. All the land cover types, except for water, showed similar trends, that is, decreasing NDVI, increasing albedo, and an increasing LST. But they differed in the magnitude of the response, depending on the land cover type. The signature differed somewhat between West Central and East Texas, depending on the dominant land cover type. East Texas had the smallest change, as it's dominated by forests and wetlands, both of which were rather resistant to change under the impact of the drought. Dryland farming and pasture land makes the biggest contribution. Note that these are both human-altered landscapes. So what we found is that when you go into an area and you take an area that was forest, or you take an area that was dry shrub grassland and convert it to farming or pasture or grazing, you make it more sensitive to drought. Not too surprising, right? You're replacing it with annual grasses, for example, with shallow roots, which means that when you get that drought coming along, it's going to be much more impacted than by a tree, for example, that has deeper roots, or a desert shrub that, while they look pretty small at the surface, they too have quite an impressive root system, making them, by their own evolution, more resistant to this kind of drought. And finally, that question about which feedback dominates, we have a clear answer to that. While the net radiation decreased due to the increased albedo, the sensible heat flux increased due to the decreased evaporation. And that, by the way, is a feedback process that also acts to link heat waves and droughts. In other words, a drought, if you don't already have the heat, you'll get it by that added sensible heat when you've shifted the partitioning of latent heat and switched that over to sensible heat. And I think I'll end there. Thank you. Happy to take questions. Yeah, Trudy.
So I was thinking about another feedback. You said that the net radiation at the surface decreased because of the increased albedo, but there was a difference in the partitioning between latent and
That's right, yeah.
heat. But as you have a reduction in the latent heat, you could have a feedback in terms of cloudiness. Right? So you could have less cloudiness, and therefore you actually increase the net radiation in the whole sky.
Right. I think that's a very important one. It's missing from this analysis, though, because all the satellite data, for reasons you can imagine, are done on clear sky days, right? You can only view, so this is the biased, what I've given you here has just the bias that you've pointed out there. These are clear sky analyses, and therefore they don't capture the effect of a change in cloudiness due to that change in land cover, which I think is probably a significant contribution. But I can't capture it here because we're trying to look at the Earth from space. That's a problem. Good point. Yeah.
The seasonal data, your blue and red curves. When you look at West Texas, it looks like there's a big shift in November, December.
Back to here, or?
Well, no, where you had blue and.
Oh, yeah, okay, right, yeah.
Yeah.
Like
Yeah.
these, for example?
So, you know, if you look at the albedo, for example, at West Texas, it looks like it's going, or.
Sorry, this is the other one. Let me get the one before.
Yeah,
The albedo is here, yeah.
yeah, exactly. So there's this increase in November in normal year, but huge decrease during the drought. What's going on there?
You're talking about that one? So that's at the end of the drought. If you look back at these rainfall diagrams, the drought actually ended in November there.
Or, you know, another way of asking my question is what happens in winter? Why is NDVI so low in winter?
You see, you begin to get some rainfall near the end of the season. It's a dry November, but it's a fairly wet October, and then December is up again. So these curves come closer together at the end of the year. But your second point was,
Basically, what happens in a normal year?
well, the red is the normal year. It's flat. The albedo is roughly flat and then increases a bit towards the end of the year. I don't know the reason for that little increase, but generally it's pretty flat across the seasons in a normal year. We could look back, Matt, we could look back and try to figure out why you get that increase there, but I don't know the answer to that.
Snow?
Yeah.
Maybe snow.
Not likely, but possible, yeah. There is some elevation there. Its elevation is about 800 or 900 meters above sea level, so it's possible you could get some snowfall in the latter part of the year.